Okay, good afternoon everyone. Welcome to the afternoon session of day 2, and this is going to be a 2 hours tutorial session. So we will do some practice on simulations. We'll teach you some tips to improve your simulation skills and all. And also we will try to learn how to build a inverter microgrid right from scratch and how to see the effect of the droop slope that we discussed today in the morning. So, you remember in the first class, the second class, I told you about the body plot of the system. In the first class, it was right, a linear system. I just showed you how to plot the body plot. So, in the MATLAB, there is a toolbox called the linear analysis toolbox. I will start with a small brief demonstration, just take 5-7 minutes about linear analysis toolbox, how to use it so that you can use it further for your studies, and then we will shift to the inverter part. So, when you talk about the linear analysis toolbox, you can make any Simulink model. For example, if it is visible here, I have made a small model like this, or like the one I had shown today in the morning. Now, what happens if you have to use linear analysis? You know what type of linear analysis we can do, like body plot, root locus, or these kind of things, eigenvalues and all, right? So, what we do when we have a system like this? So this is an open loop system. If I put a feedback from here like this, it will become a closed loop system. So the body plot that we discussed in the morning today was the open loop system. So that's why I have not made it closed loop, it's an open loop. But even if you make it closed loop and if you define the ports as open loop, it will work, not a problem. So while doing, when explaining, you can then also try at your end. It's not that 2 hours I'll continuously speaking, so you can take your time, build. If you face any problem, feel free to ask, right? So just out of curiosity, how many of you have ever used the linear analysis toolbox in MATLAB? Linear analysis toolbox, have you ever used in MATLAB? No one? So it's a new thing for all of you. Simulink. Simulink you have not done. So okay, so probably a new thing for all of you. That's good. So let's say we start with this side of a system. A step input, the reference, then I'll compare with the actual one, then the gain, the PI I showed you. What the other way of writing PI. The K and Z are the two variables that we have to find, and then this is 1 upon 1 plus S tau and 1 by CS. So as we discussed in the morning, that the symmetrical optimum method will work if you have two free S in the denominator, like 1 S here and 1 S here. Okay. So this is a simple one what we have discussed in the class today. You can make any kind of system that you like, not necessarily be exactly like this. The concept is how to use the linear analysis toolbox. It's very simple. Whatever model you make, you have to define ports. Like what is the input port, which is the output port. So, for example, you should click any arrow here, the one that is selected now, and if you right click on it, there is a option of linear analysis points. If you go to that arrow, you will find various points like open loop input, open loop output, loop transfer, loop break, input perturbation, output measurement. So like that, let's say that we write like x dot equal to ax plus bu, and then we like y equal to cx. So y is what? Y is your output, right? And if we have a step input somewhere, so we can give an input perturbation. So depending on what this signal is in your model, you can define it as the input perturbation, or you can define it as your open loop input, or if it is output, you can define it as output. You know your system, right? So depending on the system, you just have to define the port. So if I have to do the open loop analysis of this system, I define it as open loop input. So this point becomes open loop input, and you see there is a mark that has come over here. Okay, this mark shows that I have defined this as a control and linear analysis point. What point I have decided is I can just again go back to this linear analysis. Okay, you can see you can match with the symbols that are written over here. On the left hand side you have the symbols. So you can see these symbols. This symbol is basically open loop input. Alright? So if you want, you can keep doing with me, I will wait, or I can tell and then you do and ask questions and I will wait. So this is how the tutorial session will work, right? Okay. So once you define the open loop input, you also need to define open loop output. So let's say at the end of the transfer function here, I am defining again the same way. I am right clicking on this, go to linear analysis point, I am defining it as open loop output. Okay. That means from this input to output, whatever is this part, the remaining part between this becomes my open loop system. Now, for this open loop system, I can do the analysis of like whatever I want, the body or whatever. Okay. So for that, to do that analysis, what we have to do, you see the top there are icons. Different MATLAB versions may have these icons at different places, but you may find an icon which is named analysis at the top. Okay, I hope it is visible. So at the top there is this tab analysis. Now in this analysis, you see there is a tab control design. So analysis and then control design. If you go to control design, you see there can be so many analysis that you can do. Linear analysis, frequency response estimator, control system designer, control system tuner, like this. So the first one is linear analysis. Are you with me? So I click on linear analysis. Then what I have made is a linear system. If it is not a linear system, the Simulink will linearize it so as to do the linear analysis. Because if the system is non-linear, you know you have to linearize it before you can do the linear analysis. So now your linear analysis toolbox is ready with you. So you see at the top left, it is linear analysis tool, and whatever linear analysis you want, you can do. Okay. So like for example, you see here there is this analysis input output. There is a drop down box. It's a model IOs. So in the model, what IOs, inputs and outputs I have defined, those input output it will do. Okay. Likewise, you know, any system that we linearize, if it's the linear system, non-linear system, and if we linearize it, the non-linear system is usually linearized at an operating point, x0. So the stability, particularly the small signal stability of a system, is usually defined at that operating point. Okay, we do the analysis at that operating point. So therefore, you see here there is a tab with this option of operating point. By default, it is model initial condition. So by default, what is the initial conditions in the model, right? Or see, there are other options coming like linearize at, take simulation snapshot. That means, let's say you run the simulation for, let's say, 1 second, 2 seconds, whatever the time, and define the time where you want to take the snapshot. So at that snapshot, at that simulation instant, what is the operating conditions? Those operating conditions will become our initial conditions. So like that, whatever linear analysis you do, it is important to first define the input outputs, what are your ports basically, linear analysis ports. And second thing is important to define at what operating point you are linearizing the system. Right? If you have any question, please interact. Okay? So it's not a lecture, it's a tutorial, so just make it more interactive. Alright? So we define the linear analysis tools. Now you see, you can use various linear analysis tools that you know. Here you have the options, right? You can do many things. For example, in the morning we discuss the body plot. So click on the body, it will just give you the body plot, right? So someone in the morning is saying that you, what you do is to make the transfer function and then use the body command to plot body. You need not do it. Just the MATLAB will directly do it for you. Alright? So this is how the body plot will work. Okay? You can take a step response. You can do impulse response, night grid analysis, whatever you want to do, you can just try here. Alright? Okay. Let's say you do an impulse response. This is how your impulse response will look like. Right? So, these are your plots, results, and everything you can analyze here. Okay? So, let me close this. This is how it works. Alright? Let's say I remove this code. I define something new. Let's say I define this point as my step input perturbation. And let's say somewhere, anywhere, let's say this is my output measurement. So again, you have the symbols. You go to the linear analysis, control design, linear analysis. You want to see the step response. The step response, how it will look like. Alright? So, with this, I close this topic. I told this will be a small topic only. If you are interested, you can just try one or two things just to see if you are able to do it. And then after 5 minutes or so, we will go to our main topic, that is the microgrid. Okay? So I leave you for 5 minutes. You can try together, individually in your laptops, desktops, wherever you want. So I just hope, like after this session, you should be able to use the linear analysis toolbox. It will be really helpful in your analysis, in your control designs, in your studies, what you do as a part of your BTech and Tech PhD projects. In that block, the one I showed you in the morning, also, PI 1 plus S tau, and then 1 by CS. Wait, correct it. You can see the lecture notes today's class. You can try very simple 1 plus S tau, just you can try. Just to understand how to use the linear analysis toolbox. That's it. ऊपर में ये टैब नहीं आ रहे, ये वर्जन में कुछ डिफरेंस हो सकता है.
App section model linear. App section model linear.
App section. Okay. See apps and there is a model linearization. See.
Sir, in the numerator there is a j term. How to make it?
Okay, I'll tell you. Hundred e minus 6 is 1000 e minus 1000 to 10 to the power minus 6. Don't be particular about these values. Which way you can go is try to understand how to use the toolbox there. Okay, so there is one question. Someone has asked that you see the variables here k s plus z by s. How do you define the variable? It's very simple in MATLAB. If there are some parameters that you want to change during your study, you define. Don't put the exact numbers. Put the variables and go to your simulation model properties. In the model property, there is callbacks and there is the initial function. You can write all the variables that you want to define here. Okay, so initial function means whenever the simulation gets initialized, these functions will be called. So you can write all the variables that you want to initialize. So for example, here I have put k equal to 1 and z equal to 0. Okay. So it's in model properties, callbacks, initial function. तो जोर से बोलो देखो जो मॉडल हमने अभी बनाया दिस इज जस्ट लीनियर मॉडल इसको तो लीनियर करने की जरूरत नहीं तो अभी जैसे आपने वहां ब्रेक पॉइंट्स यूज किए ना हां वो हटाने कैसे वो हटाने तो उसको राइट क्लिक करो दोबारा और उसी पे ही दोबारा क्लिक करो हट जाएगा जब तक ये डिफाइन नहीं करोगे हाउ विल द सिस्टम नो व्हाट इज योर इनपुट व्हाट इज योर आउटपुट व्हाट इज योर स्टेट you have to tell them what is the transfer function it relates the input with output no so you have to tell what is input what is output okay So if you are done with this, shall we go ahead with the actual topic? Okay, how do you write this transfer function? You write the coefficients here. The first term is it's like higher order of s, higher powers of s. And the way you write it will come automatically.
Yes, this is define z. That's right.
Error. Okay, any other question? Sorry? So it may change a little bit with the version. In the MATLAB version that I have, there is an analysis option here at the top. Analysis, and then you have to control design, and then linear analysis. And here you will get the linear analysis toolbox. In the latest version, it's under apps, right? Okay. And then there is the option of model linearization. So you can go to the model linearization. Okay, so I'll go to the main topic of our microgrid. That was our main topic, right? I'll stop this one here, and I'll continue with the simulations that I want to show you, and we would like to develop this kind of model. Okay. So I will tell you a few basic things that you need to understand when we are developing a model like this. In this model, first I will tell you about the model, and then I will tell you right from the scratch how to start. So as I told you, in a AC microgrid there could be multiple number of inverters. So here is my first, second, third. Inside this block, this is actually the inverter is. You have a DC voltage source, the inverter, the LCL filter, and all those things. And then what we discussed in the lecture, the current control loop, the voltage control loop, the ABC to DQ blocks, and all those stuff. These are connected through lines, which are RL lines. Now you see, I have put two loads, one is here, one is here. When the simulation starts, the voltage builds up, the power will be given more by the source which is electrically closer, and gradually by change of frequency, the powers become same, as we discussed today in the morning. So let me first show you that thing, and then we'll go into the more details. Okay, I want to show you the whole concept first. So what I want to demonstrate here is the effect of the slope. Remember the equation, there was a slope of frequency versus power. I would like to demonstrate how the slope affects your system performance. Okay, so okay. So initially when the system is off, the frequency reference is your 314, nominal frequency 250. The system voltage starts. Right? I give the PWM instruction to the inverters. The voltage builds up. As the voltage builds up, the load is supplied by the inverters. You see here, there are three colors. This is the power on the left hand side. On the right hand side, you have the frequency, angular frequency. Now you see, this one is quite high compared to the other two. So initially, as I told, the source which is electrically closer to the load will give more power. So this is giving more power, but what this is doing is, it is limiting the other sources from giving power. The problem this may create is, this may lead to instantaneous overloading. So it is very essential that we bring them to same power. How are we bringing them to same power? By changing the frequency. So the one which is giving more power, its frequency we are reducing more. Others are having higher frequency. As the others have higher frequency, their angle, relative angle, which is the integration of omega 2 minus omega 1 dt, the relative angle increases. As the relative angle increases, the power starts to flow from these sources. Now these sources start to push power. So you see here, like this one, the color, this is increasing. What happens? Because the load is fixed, the first source has got no choice but automatically to reduce its power. So its power starts to reduce. As its power starts to reduce, its frequency starts to go up, while the other frequencies start to go down. And now, they become same at some point. So frequencies become same. powers become same. This is how the primary control and group control works. The problem with this is now there is a deviation in the frequency. For that, we need the secondary control. But for time being, we will not discuss the secondary control here. What I will demonstrate more is the effect of the group slope. So, just keep these numbers in mind for the sake of it. For example, the first one reached here 6,000, and these become same at almost 1.8. Okay. Now, let me stop the simulation and let me change the group slope to show you the effects. Okay. So what I'm doing is let's say I decrease the slope variable, the gain. If I make it smaller, let's say I make it 10 times smaller, minus 6. Just one number I have changed. The slope I have made it more flatter. So the slope now is more flatter. If it is more flatter now, what will be the impact? The frequency will change slowly because it's more flatter. The frequency kind of remains flat. Flat means close to the nominal frequency. What that means is there will be less frequency change. In a way, it's good for the system that the frequency change is less. But the effect will be, because the frequency change is less, the integration omega 2 minus omega 1 dt, that angle will change very slowly. The angle changes very slowly, integration omega 2 minus 1 omega 1 dt. What will happen? Power flow, P equal to AV by x sin delta, that power flow will be slowly increasing. So that means the one which was giving higher power will continue to give higher power for a longer duration. It may lead to even more overloading. Okay? So let's see this. I told you the number. Initially it touched 6,000. Now it has gone nearly 6,500. So, because others are slow to respond, the slopes are nearly flat. If you make it slope 0, absolutely flat, these will not even respond. Right? And then what will happen, you see, it will take a lot of time for these to actually converge to a single point. Right? So, definitely being flat is good from the regulation point of view, that you are getting well regulated frequency. But it creates the problem that it may lead to unnecessary burden on any of the sources. Right? So then what we have to do? Let's go the other way. Try to make it steeper. And rather than keeping it flat, let's try to make it steeper and see what happens. Right? So I'll stop it again. And I will change the values again. So from the original value, let's say I increase the slope 5 times. 5 times the slope is increased. If so happens, now what will happen? Now it is becoming more steeper, that means the frequency will change quickly. If the frequency changes quickly, the integration omega 2 minus omega 1 dt, that is the angle will change in a relatively faster manner. If the angle changes in a relatively faster manner, your power flow P equal to EV by x sin delta, the power flow becomes quicker, the change of power becomes quicker. So therefore, others will try to match it very quickly. You can see now it has come down almost to 5,000. Okay, but the effect is the frequency has fallen more, so the regulation has become more. All right. And then there is one more thing. If you remember today's lecture in the morning, I talked about the control system stability. In the control system stability, I told that the power controllers introduce low frequency oscillations. As you make it steeper, you increase Do you see some oscillations? These are called low frequency oscillations. Okay. So these oscillations have you have observed these oscillations only because of your controller gains. Nothing else has changed in the system. The source is the same, that the parameters of the distribution network is the same, the load is the same, perturbation is of same magnitude. The only thing that has changed is the slope that you have introduced in the controller. And that is why this type of oscillations that arise, these are due to the controls effect, and that's why it comes under the purview of control system stability. But again, every coin has two faces. The better part is, you see now they have matched, they have become equal powers at almost 1 second. Previously we saw it was around 1.8, so the time has reduced. But the problem is the frequency has fallen more, that means the regulation has become poor. Regulation is one thing, but these low frequency oscillations, these may actually become unstable and they destabilize the system. So I will show you this thing. If I increase it 10 times instead of 5 times, so this is where the firing pulses start. And you see, now it has come even lesser than 5000. They are almost same powers. But then what will happen over a period of time, those low frequency oscillations would become unstable. The whole system will become unstable. So I hope you realize the importance of just one single parameter of a system. Okay? You see the oscillations increasing, the magnitude of the oscillations increasing. The whole concept is, with the slope increasing, your system is getting more closer to instability. This comes under the purview of control system stability that we discussed today in the morning. Alright? Okay. So this is what I wanted to demonstrate you. Let me stop here. And now we all try to build this model right from scratch and see how much we can learn in the remaining 1.5 hours. Okay? So what we should do? We should start to build the single inverter. Once we make it, it's very easy to just copy paste and connect and make 3. But before that, I would like to discuss few things with you. Whenever you do a simulation in MATLAB, it is very important to define the simulation settings very clearly. If you do not put your settings clearly correct, your simulation is never going to give you correct results. So, it's a software. The software doesn't know what to do. Whatever you just say, it will do. Whether that is logically correct or not, it doesn't. So, few things you have to consider very carefully here. If you go to simulation settings, any computer you can try it. You see, there is a solver section. Simulation settings, there is a solver section, selections. And that solver gives you option fixed step or variable step. So it's my recommendation when you do these kind of simulation studies, always go for fixed step. See what happens usually, we do the simulations, we think we are getting some results, but most of the times it happens those results are wrong. And why those results are wrong is just because you have not done the simulations in proper setting. Okay? So, what are those settings and why they are important? Is particularly the step size, Now what happens, these simulations are done in discrete individual steps. These are digital calculations, right? So you take a sample means your measurements, voltage, signals, whatever the signals are. You take the sample. Once you take the sample, the computation is done. Okay? Once the computation is done, numerical computation, the whatever output you are expecting is observed. Same is done at every next sample. Okay? Now what happens if your sampling is not done properly? You will not get the correct response. For example, you have a sine wave. Let's say you have a 50 Hz sine wave, 50 Hz. What is the time period? 20 milliseconds. Let's say I sample it every 10 milliseconds. Can you visualize a sine wave sampled at every 10 milliseconds? That means at t equal to 0, or omega t equal to 0, omega t equal to pi, omega t equal to 2 pi. That means you are doing the sampling where? At 0, next 0, next 0. If you do this kind of sampling and you run the simulation, what would you get? You will get 0, 0, 0 connected by a straight line. So what MATLAB does is, it does the sampling, calculation and connects them by straight lines. So 0, next 0, next 0, it will plot you a complete 0 line. So now the question comes, you are expecting what? You are expecting a sine. What you are getting is 0 line. Is it the fault of the simulation? No. It's our fault that we have not done the sampling properly. Let's say we go ahead, one more step. Instead of 10 millisecond, this 10 millisecond 0, 0, 0, what if I simulated 5? 0, 5, 10, 15, 20. You have 20 milliseconds one cycle. First sample at 0. Next at 5 milliseconds. What value you will sense? The peak. Then 0. Then negative peak. Then 0. What will you get? A triangle. Okay. So that is how your sampling is important. To have a proper smooth sinusoidal waveform, you need to have a proper sampling sufficient enough so that you can recreate the sinusoidal signal. Okay. So it is always advisable to put a correct sampling number. Now MATLAB gives you an option of variable step. That means MATLAB by itself can decide what should be your sampling time. But that is not always a good option. Why? Because what MATLAB does is, when the MATLAB feels the system is not changing much, it increases the step size if you use a variable option. When the system changes fastly, it reduces the step size. For example, you have a sine wave like this. Initially, it is more of a linear region. So if it is initially in the sine is like this, so around 0 it is more of a straight line. It is more of a straight line, you can take larger steps. When it becomes this curved nature at the top, the numbers are changing quite quickly. Like d by dt is positive, d by dt is 0, d by dt is negative, like that. So suddenly, there you need a smaller step size. So what happens then? The MATLAB will start to reduce the step size. But obviously, by the time it starts to reduce the step size, 1 or 2 samples have been left. And again, you come in the linear region, in the negative half cycle, you start again the MATLAB will start to increase. And again, the same thing will happen. So this is where you don't get a proper waveform. So it's good to have a fixed step size. So I always tell students to, whenever you do some simulation, make sure you are always done with these settings correctly. Otherwise, you devote your 1 year, 2 year, 3 year, you may take thousands of results, none of them will be correct. So it's very important. So you can put a fixed step size. You can choose a solver, you can choose any solver, ODE3, ODE8, some numerical solver that solves numerical differential equations and all. And then there is because you have chosen the fixed step size, what should be that fixed step size? Okay? That is important. How do we define this fixed step size? this becomes a very challenging task, because the smaller it is, the accurate it is, but then it will make your simulation very slow. The larger it is, the simulation is fast, but you get an incorrect result. That is why you have to have a simulation step size that is able to consider even the smallest period in your simulation. Now, for example, in a simple thing like this, you have a DC source, you have an inverter, you have a filter, and you have a load. Let's say you are generating the PWM signals. As we discussed in the morning, someone asked about PWM thing question. I told time constant. RL time constant, I told typically is in the range of 4 milliseconds, 5 milliseconds, 2 milliseconds, some milliseconds. But what about the PWM? For example, let's say you are doing the switching at 10 kilohertz. If you are doing the switching at 10 kilohertz, let's say, and what is the time period? Can tell me someone? 10 kilohertz means what is the time duration? So can you give me a number in microsecond or millisecond? Something like that? 0.1 millisecond. Okay. Now you see, okay. Now you see, we talked about RL time constant in the order of 2 to 5 milliseconds. This one is coming in the order of 0.1 millisecond. This is the time period of the PWM. Okay, switching frequency. That means so fast your samples are getting changed. Okay. Now, within this duration, okay, you see what is this 10 kilohertz means? You have a carrier which is of triangular nature, having a time period of 0.1 millisecond. Within this 0.1 millisecond, do you know how the PWM pulses are generated? You have a reference signal, you compare which is higher or lower. Definitely it will intersect at durations even smaller than this 0.1, correct? So you have a sine and you have a triangle and it will intersect somewhere. The intersection could be for a very small duration. So let's say the intersection is even for a small duration. The value which is higher, for which you generate PWM 1 or 0. So you are generating for a duration of how much? 0.0, let's say 10 times if I take, for example, 0.01 millisecond. Right? So that means you have to have a system that can detect so small changes in so much small time frame. That means the system itself has to run at a simulation where it can sample these small changes within this small time frame. And that is why your sampling has to be at least smaller than this number. Okay, that is one thing. Second thing is another very important, which many people miss and don't then understand what is going wrong with your simulation. The sampling time that you choose and your system fundamental period, those should be integer numbers. Okay. So, what happens if these are not integer numbers? What I mean is, for example, let's say you have a sine wave. You start with the 0 of the sine wave. Your sampling instant should be such that the next waveform 0, exactly the same place it should be sampled. Okay? Otherwise, what would it feel? Let's say you have a sine wave. You are taking 10 samples. So first sample, second sample, third, fourth, fifth, sixth, 5, 6, 7, 8, 9. The 10th samples should be perfectly aligned where the first sample was. Right? Or maybe 10 if you are taking per cycle, then the 11th one should be at the same location where the first one was. If so doesn't happen, if let's say you don't align your samples properly, then what will happen? The next cycle, first sample will not start at absolutely the same point 0. Are you with me? So it will happen that within one cycle the system would feel that something has changed, although nothing has changed, right? So that is important. Your system number of samples should be such that the samples align properly. That's why the fundamental period should be an integer multiple of your system sample time. Okay? If you consider all of these things, you decide a proper sampling time, then you do the simulation, then you can think that okay, your simulation results will be correct. Otherwise, you just keep doing something and you may get some results, but all those results will be wrong. Okay? So that is why here, in like for example, my case, I have put a simulation sampling time of how much it was here. 0.625 microsecond. 0.625 microsecond. Because probably I have taken a switching frequency of 8 kilohertz. You have to see. So 160 into 50, how much it is? Yes. Eight kilohertz. Okay. So that means the period of this 8 kilohertz should follow that integer number. So that is one thing. So that is always the thing, you have to have a starting point. And then when you do sim power system components, that means electrical system components, you have to put a power GUI block. Again, the power GUI block gives you two options: discrete or continuous. What are these things? I will tell you later. Discrete simulation, continuous simulation, what is the difference? But we have to choose this discrete simulation, and here also it asks the sample time, and this sample time should be same as the sample time that we have put in our simulation sample time. Okay, so this is the sample time of the simulation, and this is the sample time of solving of electrical components. Correct? So this is how you start it first of all. So when you take a blank simulation, you first make your simulation ready. That's the first thing. Then you start building it. So we have almost 1 hour, more than 1 hour. Try to work with me, try to build it. Try to start with one single inverter. How will the one single inverter look like? Now we go into the inverter. Okay. You have a DC source. Now you can take any number, don't bother about the numbers so much. I have taken 1200 volts, you can take 1000, 800, 700, 900, something like that. You can take a number. Connect with a bridge. This block is a universal bridge. Universal bridge, and you can select the number of arms. So the same block can be designed for single phase, 3 phase, depending on the number of arms you take. And also the type of power electronic device you take. IGBT, diode, thyristor, GTO. So usually for PWM inverters we take IGBT, MOSFET, these kind of things, right? So you have IGBT diode. Okay. So you have the DC source, you have the IGBT diode, you have the LCL filter. So you see you have this RL with 0.1 resistance, LF, filter inductance. You can take in the order of 1 millihenry, 1.5 millihenry, something like that. You have a capacitor, LCL. The capacitor are taken in the range of 50 microfarad, I think, something like that. And then another RL. This is quite small, I told you. So this is 0.03. Much smaller, you can neglect it also. So you can take a filter of, like, the previous one was 1.5, this could be 0.3, 0.2 millihenries. Okay. So this is the electrical circuit. The electrical circuit is just like this, only this much. If you remember today's lecture, DC source, inverter, LCL, and the load. That's it. You can connect the load here. Okay. I have made a subsystem. Not necessary to make a subsystem. You can just connect the load here. So this is the electrical part. That's it. Electrical part is this one. Source, inverter, LCL, and load. That's complete. Now, what remains is the control part. Control is very complicated. So what I request you guys is just keep working, be with me, do step by step, and tell step by step, and let's see how much we can finish in the remaining 1 hour. Then you can practice at your own bit. At least I will give you the tips. Okay. So start with this. Try to make a model. I will zoom it a little bit for your reference. Okay. So this is like this. In the universal bridge, there is a signal G at the top. This is where you connect your PWM signals, the gate pulses. And in between, because for controlling we need the measurements, the currents and the voltages. So we have these blocks, VI measurement, 3-phase VI measurement. I have used more than required, no need to copy it exactly. So basically, what do? We use the IL current, we control this current, right? So we need a current measurement from here. We have to regulate this voltage, so we need a voltage measurement here. Finally, what is the power delivered at the output? Is this voltage multiplied by this output current. So therefore, we need a current measurement here. At least this much we need. And this is how your system will work. Basic system. Okay. So, what I recommend at this point, you start with this. At least make this much part. To see what settings you need to do, the simulation settings, the block sets. Are you able to use them like that? Then if you face any difficulty, ask me. Again, I am saying no need to try to photocopy this block that is there. There are more number of measurements than needed that I have put here. Understand the concept. You need to measure the current for the first inductor. You need the voltage across the capacitor. And you need the current for the second inductor. That's all you need. You need these measurements. That's it. And even before the measurement, you have to make the electrical circuit, completely electrical circuit. And most of you are MTech PhD students, so I know you know basics of some simulations. You might be using MATLAB, right? So you just have to put it. After this, you can just put a simple load like this here, this block, 3-phase RLC load. Now make sure whatever elements you are putting, you put the correct values. Very important. Okay. For example, when you put a load block like this, 3-phase parallel RLC load, by default it will have some values. Those values may not be suitable for your system. For example, you are developing a 400 volt AC system. Then your nominal phase-to-phase voltage should be a 400 volts. Its default value could be a 11 kV, something like that. Don't do those things. Don't leave them as it is what they are. Whatever block you are putting, make sure you put the correct value to it. So I have removed the other accessory things, and this is what I am expecting at this point. We start with a very simple basic model. Which block? That means this block. This block is 3-phase VI measurement.
Is that the product the roadside inductors? Roadside inductor of the LC filter. There is a block coming out after the scope. Is that a product block?
Yeah.
जो स्कोप के बाद जो ब्लॉक है ये उसके पहले वाले ये उसके पहले जो है वो जो ब्लॉक ये हाईलाइटेड है हाँ उसके बाद थोड़ा ड्रॉप किया है वो ये
RMS. Here's the RMS value. RMS. उसकी जरूरत नहीं है, उसको तो छोड़ दो. अभी के लिए So this is what, in a very simple way, I have shown. At least this is a basic that you have to start with. And also, you have to put this power GUI block, and then put all the time constant settings and all that are required. Okay. So what is the status? हाँ PW का
उसके बाद कौन सा
ये
PW जनरेटर
ये हाँ हाँ उसका यहाँ ये वाला सारा हो गया डीसी सोर्स से लोड तक का
वैल्यूज नहीं मिल गया
वैल्यूज के साथ डालो So, I hope in the next 5 minutes everyone will be able to at least make only this part from the DC source to the load. Only this much part with all the values. These inductor values, I am saying RL 0.1 ohms and like 1.5 millihenry you can take. Capacitor value you can take around 50 microfarad. And this you can take even very small resistance and very small inductor like say 0.5 or 0.1 millihenry like that. Then put the load values, the rated voltage 380, 400, 440, whatever, 50, and the active power that you want, 5 kilowatt, 10 kilowatt, 12 kilowatt, whatever is you want. Okay. So, source, put any value, 800, 900, 10, like 1000, 1200, 1100, 1200, doesn't matter. Okay, so if you are done up to this point, please let me know. If not, we can spare a few more minutes. Kiska? See, you can put any value of your choice, like circuit number, 1000 volt, 1100, 1200, 800, 900. Then this inductor, first inductor is 1.5 millihenry, you can put, this is 0.1. This one you can put around 50 microfarad. Next one you can put even smaller, like 0.03, 0.2, 0.3 millihenries, like that. Okay. Load values you can put any value of your load you want. Just make sure the frequency and the voltage, nominal voltage, are put correctly. Once you are done with this part, then I will tell about the PWM part. Okay, so any one power jewel just once in the system. Once you put power jewel at one place. So, alright, shall we go ahead? Let's see the PWM part and then I'll tell you the control design later. Okay. So for now, I am starting the open loop design. Open loop design means there is no control action. You give a firing pulse at a fixed modulation index. Okay? At a fixed modulation index. That means whatever is the modulation index, accordingly you will get some voltage. But you don't have any control over that voltage. But let's see if we can make a system work at least in open loop. Okay? Once we can make a system operating in open loop, then we can try to make it in closed loop. So how does the open loop system works? This is the electrical part that I told you to make first of all. Then here the input is the gate signals, the PWM. Okay. So for that you have to put a PWM generator first of all. So this block that you see here is a PWM generator. Now different MATLAB versions may have different type of these blocks. You may find it little bit different color or name or something. But in the PWM block, just like the universal bridge, you can select how many switches. So like 3-phase, 6 switches, right? So there is 3 arm bridge, 6 pulses. And you have to tell the carrier frequencies. For example, I am doing at 8 kilohertz, so I put 8 kilohertz. Then it will ask us sampling time. Sampling time is your system sampling time that you put whatever, like I put 0.625 into 10 to the minus 6. So that sampling time you put. Okay. So in this PWM block, there is one input which is UREF, one output which goes to the gate signal. Now, just add one block unit delay. Why this block is needed? Because when the simulation starts, from where it will start, it doesn't know. So just we put one sample delay, so all the signals are passed after one sample. It's just a trick to do some simulations, nothing much in this. And then here I put a product block basically to tell when to start the simulation. For example, I have done it from at 0.15, 0 to 1. That means my PWM will go into the inverter at 0.15 second. You can change any time, you may not, you may even remove this block as you want. Okay. So first thing is, you have to have a PWM generator block whose output goes to the gate signal. That's it. Now, what is this PWM generator block? You know the PWM generator blocks takes into as an input as one reference signal. 3-phase means 3 reference signal 120 degree apart and one high frequency carrier. High frequency carrier you have already defined 8 kilohertz here. Now the thing is, how do you develop, how do you get your 3-phase reference signals? Now to get 3-phase reference signal, remember this block diagram and just see this last part. You have D-axis modulation index, Q-axis modulation index, 0 is your 0 and you give a theta. And I told you this theta for autonomous mode will come from integration of a constant number because the same, it will produce its own theta. Alright? So integration of this constant number will give you a theta. That theta you will put here as an input and you will get DQ0 to ABC conversion block. Then you will get MA, MB, MC, basically 3-phase reference signals, right? So this is what we are doing here. You have fixed modulation index MD, MQ, M0. Ideally these MD, MQ, M0 they come from this whole control law. So I am not putting the control law. That means I am doing the open loop design. So what we are doing here is we are putting a fixed number. MD, for example, I have put as 0.7. You can put any number. 0.7, 0.6, 0.8, 1. Maximum is 1. MQ0, M00. Then we mux them. Mux them, so signal goes in the form of DQ0. Now DQ0 will be converted to ABC. This ABC will go to your PWM reference signal and PWM will be generated and will go to the. Now only thing is this DQ0 to ABC block. This DQ0 to ABC blocks need that theta, which comes from the integration of omega. Now again, depending on MATLAB versions that you are using, somewhere you will find as theta input, or somewhere you will find sine underscore cos just written here. So in some versions it takes sine theta and cos theta as an input. In some version it just takes theta input because you know the matrix. We discussed this today. The matrix has cos theta, sin theta terms. So either you give cos theta, sin theta depending on the version you have, or you give just the theta. How do you get the theta? Now you get the theta by this. You have the nominal frequency, a constant, which is your 2 pi 50. I used a variable, you can give it a number 2 pi 50. Then you integrate it. This is your theta. This angle is your theta. If your DQ to ABC block takes theta, you can give theta directly. But there is one suggestion, put a unit delay. Just like you have put a unit delay block here, also put one unit delay block here. Okay, so then I can say this is my theta. Theta conversion. Okay, so if your block, what happened? If your block takes theta directly, you give this theta directly. If your block takes sin theta cos theta, then get the sin theta, get the cos theta. So you have a block called trigonometric function. You double click on this, you select the function sin, cos, whichever you want. Okay, sin theta, cos theta, you mux them and give as sin cos. So basically now your system is ready in open loop. Now when you run the system in open loop, run the simulation, at what time you give the PWM, accordingly the voltage will develop, right? So for example, I have given the PWM at 0.15 seconds. So at 0.15 seconds, I will start to see a voltage here. As soon as I see the voltage, I will also see a current. And this current will depend on the load value I have put. For example, I have put 5.8 kilowatts. You can put 5 kilowatt, 10 kilowatt, your choice. Just put the value voltage properly. Okay. Once you do it, you will get this three-phase voltage. You see, this is my three-phase voltage, sinusoidal, and this is my three-phase current, sinusoidal. Obviously, there will be some harmonics because of the PWM switching. Okay. So like that, now I am getting a three-phase output voltage and current. The only thing is this three-phase output is not regulated because we are giving a fixed modulation index. If we change the modulation index, for example, if I let's say change it, if I make it 0.9 instead of 0.7, you see my voltage can change. So this what I've done manually. What the controller will do? The controller will automatically find the correct value of this modulation index MD and MQ so as to get the desired voltage that we want. What do we want? We want our whole voltage should be aligned along D axis and our Q axis voltage should be 0. So that task will be done automatically by the controller. So this is how the open loop system is working. Whenever you make a control design, first you have to check whether your open loop system is working or not. Unless your open loop system is not working, your closed loop system will not work. So this is where I stop now. Again, I give you 10-15 minutes. You try to develop up to this point. See if you can develop an open loop system, autonomous three-phase inverter. Then will be the most difficult part, which is the closed loop. So we'll take the closed loop design at the last. Start working. Give the PWM signals. Generate your inverters firing signal. Get the three-phase AC quantities, voltage and currents.
How the sign was works after the how the trigonometric functions work after the
So if there is built sine function, it is. We just use a whatever like sin x, y equal to sin x function.
after the unit are they going to the trigonometric function both of the additional
Sorry.
after the trigonometric unit is it going to both
Or both. With the same signal going to the both now. With the same signal going to both. Sin and cos. What is that? This law. Some version it will take theta directly, some version it will take sin theta and cos theta. So two inputs, sin theta and cos theta. So 2 to 1 you have to use a mux. So this is sin x, this is theta, this is sin theta, this is theta, this is cos theta. You mux them, you get sin theta muxed with cos theta, and you put it there.
I am asking what is the name of that law?
That block dq0 to abc. The dq0 to abc transformation.
How do you modify it to take it in the equivalent?
I didn't modify this. As I'm saying, it's version to version. Just search this block dq0 to abc and just see what block you are getting. I'm writing the numbers here. You will take around these numbers. It not necessarily exactly this number. You will take around these numbers. these are the numbers. Whatever number you take, just make sure your step size follows the relation I have told. These are the basic numbers to give you an idea. See, with playing little bit is the filter parameters, your results may change. Some harmony may change. At least you should get some results. This block is DQ0 to ABC transformation. ABC transformation. We have half an hour left. Let's try to proceed further. And I hope you can practice at your respective places and try to learn it. Okay. So now, first step is open loop. Second step is getting the correct measurements. And third step is to make the closed loop. Okay. So when you have the measurements, we will take measurements across this. So this current is basically IL that will go in the control. This current which is here, so here also you put a measurement. Okay, here also you put a measurement. And this current is output current, IO. The output current multiplied the voltage will be your power. So power calculation, active and reactive power calculation, you use IO. For control purpose, we use IL. And the voltage from here is VO, output voltage. Okay. Now what we do is, we check whether our measurements are correct or not. So what we'll do, we will take these measurements and we will convert them from ABC to DQ, try to calculate power. Okay, this is our basic measurement sense, right? So what we do, you remember this block? We need these things, right? ILD, ILQ, okay, VOD, VOQ, these things, these variables are needed, right? So what we are going to do is, in this simulation, we will take these measurements IL, VO, IO, and we will convert these measurements to DQ quantities. Okay? So just like you have DQ to ABC here, we'll take the reverse, ABC to DQ. Okay? So let me take the ABC to DQ block. So ABC to DQ block looks absolutely the same, it's just reverse, input is ABC, output is DQ0. Okay? Now, see, this also takes the same sin theta cos theta, or it will take the same omega t, the same signal. So what signal you have used here, na, sin theta cos theta or omega t for that matter, same you have to use here. Okay? So I connect the same signal here. And I am making 3 of such. Why? Because for the IL, for the VO and for the IO. So I connect here the 3-phase quantity IABC. Correct? Then same way I connect these two, and this one I connect to the voltage measurement, so VABC, and this one I connect to the current measurement IO. So now basically what I have got is IL in DQ, VO in DQ, and IO in DQ. Okay? So if I put scopes, let's say this is DQ0, current, voltage and current. So I have got the dq0 of the 3 variables. Now if you run it, so the signals that we have received, that the AC variables, those AC variables will be converted to dq0 quantities. Okay. So first we will get the dq0 of the inner current IL, then dq0 of the output voltage, and dq0 of the output current. Okay. So this number that you see is 0. Is can't be readable, is 10 to the power minus 17. It's basically 0. Okay, 10 to the power minus 17 is 0. Now you see, once we have started the PWM, we have got these numbers. This is my ID, this is my IQ, and this is my IQ. You expect them to be DC quantities, but they will have ripples because we are doing PWM switching. So definitely there will be ripples. So those ripples will be reflected in DQ quantities. Okay. So this is my ILD, ILQ, and IL0. Likewise, my voltage. You see, again there are some ripples, right? It has to be there. This is my VOD, VOQ, VO0. Now what we actually want, we want all the voltage to be aligned along the axis, so VOD should be the number and VOQ should be 0. But you see here, our VOQ is non-zero. Why? Because we are operating in open loop. And VOD is also, you see, at some number, random number. And we don't know whether this is the required or not, because again we are operating at open loop. Okay. Likewise, output current. Output current, IOD, IOQ. Output current will have definitely less ripples because the high frequency current component passes through the capacitor. So the output side is more filtered, right? So therefore it is less ripple. So you have IOD, IOQ. Now when we measure the power, we measure voltage into output current. So output voltage into output current. So the last two we use. While we are in the control we have ILD star, ILQ star. There we'll use the first current, this current measurement. Okay. So now let's see how do we measure the power. Okay. So what we do, we know the formula. Power formula we already discussed. It's 3 by 2 VDID plus VQIQ, right? Active power is this 3 by 2 VDID plus VQIQ. So I'll just calculate this number. Here you have VD, VQ, here you have ID, IQ. So what I'll do, I'll first demux them. Okay. So I demux them, I get VD, VQ, V0, 3 signals. Likewise, I get this one, okay, which is my ID, IQ, I0. Now you know the formula, VD into ID plus VQ into IQ. So what I'll do is I use a product block. So it is VD into ID and VQ into IQ, then a sum block to add them. So VDID plus VQIQ and a gain of 3 by 2. Okay. So a gain block 1.5 put. This is my active power computed, right? Now again if I put a scope, this will tell me what is my active power. So I put my active power here. Now if I run it, I should get a constant number of active power. Because active power is constant, three-phase active power is constant. So let's see if we get a constant active power here or not. Initially it is 0 till we give the pendulum signals. Now this is my active power. I am getting a constant active power. With some variables would be definitely there. Okay. Now to remove these ripples in the control design, what we do? We put a filter. And you saw the instability problem? That is actually due to the filter. Because filter introduces always a low pass filter will introduce a lag. A lag makes our control slow. That leads to instability. So if we have to plot the filtered one, what I'll do? I'll pass this calculation through a filter. That will be my filtered power. That is my variable P that I will use in my droop equation. You remember the droop equation, omega equal to omega nominal minus MP minus P naught. For simplicity, let's say P naught is 0. So omega equal to omega nominal minus M into P. Correct? So what I'll do is I'll take that filter block from here and I'll take that MP, the gain block. Okay. So this is a filter. First order simple transfer function filter. And now I pass it this value and I put another scope. Okay. Now let us again try to see what effect the filter makes. Okay. If you don't put a filter, you will see noise, ripples, and you will see sudden large changes. Let's see. So this is my unfiltered power that we just saw little while earlier. You see the power changes suddenly as soon as you give the pendulum signal, but it leads to a very high noisy signal and there is ripple over here. Let's plot this one, the filtered one. You see it increases gradually. And this is the lag the filter introduces. And this lag leads to instability. But at the end, they will converge to the same steady state value. Okay? For example, this is converging to a value around 18,000. You see this one is probably should be around the same number, 1.75, it will be the same. Okay. Now why it is 18,000? Why it is not the value that we have kept here? Because this power will come when the voltage is at this value. When you regulate the voltage, currently the voltage is not regulated. So you have high value or low value. Accordingly, the power will V square by R power will change, right? Because the voltage is not regulated. Okay. So now you see. Like this, what we have done is, we have calculated the power. Now you know, so see step by step we are building the complete closed loop of the single inverter. We calculated the power. Now what is left? The droop, the voltage controller and the current controller. This is what we discussed. If you remember, from here, you see, the voltage controller VOD star minus VOD, like that, the current controller, and what we get is this VD inverter, VQ inverter, we then multiply by 2 by VDC to get MD, MQ. Those MD, MQs are here. So once we put the whole controller, we will just disconnect from here, that's it, and we'll put that controller. But that stage we have not achieved yet. We are going step by step. So let's first see how the droop works. Currently the system frequency is nominal frequency 50 Hz because we are integrating a 50 Hz signal. Okay. Now you know the droop equation. Droop is omega equal to omega and nominal minus M into P. Let's say P naught is 0. That is what we have to do. So omega nominal minus, let's see now, let's try to make it droop here. So we take a sum block again and you make it plus and minus. Okay, so omega nominal minus, and what do we subtract? M into P. P is the power, which is the filtered power, correct? So you see, this is my filtered power, and I have this M block. I just have to multiply. So I multiply this. Okay. So M into P is now obtained here. This becomes M into P. This M into P I will just subtract from the omega nominal. This becomes my actual omega. So now my actual omega will be different from 50 Hertz. Okay. So again I can put one scope here. And again I can run it. Okay. So let's see the scope result. Till we do not give the firing signal, there is no power output. My omega is same as our nominal omega, which is 2 pi 50, that becomes 314 radian per second. So you get a number 314 radian per second. As soon as the power starts to increase, frequency starts to drop. And it will drop based on the value of M that we have. So, because it's a single inverter, there is no issue of instability. Because there is no relative oscillation. Oscillation always occurs with respect to some other. So far, I am just showing you a single inverter. Just like you had, there will not be any oscillation. But this may happen if you have two, this value may be unstable. So then you have to reduce the amplitude. Okay? So this is what we have done. We have now implemented the truth part. Okay? Now what is left is the very simple part. This part. Sorry? No display. Ajit? The only thing that is left in the design of a single inverter is the voltage control loop and the current control. Now you see you have the voltage control loop here. First you give a D-axis voltage reference. Now what is a D-axis voltage reference? Is depending on what type of ABC to DQ conversion we are doing. As I told, it could be your phase voltage peak, it could be your line voltage peak, it could be your phase voltage RMS, line voltage RMS. So the ABC to DQ formula that you are using, so if you go inside the mathematics of this block ABC to DQ, how it is doing, just see inside this. You can see the formula that is being used. Okay, study this. You will understand which type of ABC to DQ conversion it is doing. Accordingly, you have to put a constant number as the reference. Just like here, if you see what I have done is this. This is my V nominal. Okay, V nominal. Here I have put a number which is I think 380 or something. Okay, so you put a constant number that becomes your VD star. Then subtract from it VOD. VOD is already available with you. What you have done is here you have two signals. This is VOD and this is VOP. So you can just take this signal to that subtraction block. PI controllers, KP plus KI by a simple PI controller, and you can tune the value. We have discussed one method that you can use to tune the value, or you can in the beginning try with a hit and try approach, or maybe you can read some literature, you can see what are the appropriate values, you can put those values. This will be my, this signal will be my UD, D-axis control variable. Then there is a speed forward term. You see here now there is a small difference. This is IOD, while this reference is ILD. Two currents we are taking, right? So in the simulation, this one is my IOD, while this one which is coming from the first inductor, because this is coming from the first inductor, right? So this is my ILD. This one which is coming from the second inductor, this is IOD. Correct? Now what you have to just do, you have to follow this block set. VOD star, VOD, VOQ star 0, VOQ, omega you know 2 pi f, C you know 50 micro that you have put. Again PI controllers you can just put. Then you can add and subtract. Feed forward gain, as I told in the class, usually it is, ideally it should be 1, but usually it is less than 1, so 0.7, 0.8 you can put. This will be your ILD star. Likewise you will have here ILQ star. From this you subtract ILD and ILQ, which you have already got here. ILD and ILQ demux, just like you have done that demuxing. ILD, ILQ. Once you demux, then you get ILD, ILQ, then multiply by omega L. Omega L multiplication is the first L, because we are controlling the current through the first inductor. Right? This one. This L value you know what you have put. 1.3 millihenry, let's see if you have put. So you can use that. So omega L, then get multiplied, then you get VQ inverter star and VD inverter star. What you do after this then? We go back to this design. VD inverter star, VQ inverter star, right? And then what you do? Multiply by 2 by VDC. So just take a multiplication block, 2 by VDC, just multiply. What you will get is MD, MQ. This MD, MQ is what we have used here as the constant blocks. You just have to delete this and connect your controller MD and MQ here. Like this, your overall control of a single inverter with power control, voltage current and control will be complete. Then you see whether your voltage is actually regulated or not. Like if you see your voltage here currently, what is my DQ voltage? As I showed you, currently the Q is non-zero. But once your controller will work, you should get your VQ as 0 and VD as the reference that you set. If that is done, your single inverter is complete. Then what you do? You copy it, make a copy, you get the second inverter. Let's start with 2, don't go for 3 from the beginning. And put a line in between, just like line, RL line. Put the values again, R and L, so you will have microgrid with 2 inverters. Then plot P1 and P2. You see whether you are getting the equal shared power or not. Alright? So, we have done up to a greater extent in today's tutorial class. We couldn't finish the internal control loop, but that's very simple because now you know how to get the signals and what signals to get. Once you get the signals, you just have to absolutely follow this block. Clear? Any other question? So we can take last 2 minutes, it's 5:38, let's close at 5:40. If you have to ask any question on what we have done, and if you want to clarify something, just let's take 2 minutes and then we'll close it today. Okay? Anything from anyone? Alright then.
The output from the group.
Huh?
Why is it going?
The output from the group.
Yes.
So you see here what you are doing here is this. Omega directly integrated as theta. Now when we put group, the same thing, integrated to get theta, but it's just not omega directly going, it's omega nominal minus the group term. This is your new omega. So this is my nominal omega. This is my actual omega. That's it. Which is your nominal minus this signal. So this is your new frequency. You integrate this new frequency, you get the angle. Okay? Alright? Let's close it for today. I hope you have got some idea. At least you couldn't complete it, but at least you understood. Maybe you can try at your own level. Okay? Any questions? No? Alright, thank you.